A language model answers questions. An AI agent takes actions. An AI agent is an AI system that can perceive its environment, plan a sequence of steps, use tools, and execute actions autonomously to achieve a goal, operating over extended periods without human intervention at each step. In this video, we explore what distinguishes agents from chatbots, the core components that make them work, and where they are delivering real-world value today. Let us examine what makes AI agents fundamentally more powerful than conversational AI, and why the shift from answering to acting represents a genuine leap in capability. 5 core properties define an AI agent and distinguish it from a standard language model deployed as a chatbot. The perceive-plan-act loop is the architectural signature of an AI agent. Unlike a chatbot that receives a prompt and returns a single response, an agent continuously cycles through perceiving its environment, reading tool outputs, user messages, and state, planning its next action based on what it observes, and then acting by invoking a tool or generating a response. This loop repeats until the agent judges that the goal has been achieved. It is this iterative, goal-directed behavior that separates agents from the stateless question-answering pattern of conventional language model usage. Tool use is what gives an AI agent its ability to interact with the real world beyond text generation. An agent equipped with tools can search the web for current information, execute Python code to perform calculations or data analysis, call REST APIs to retrieve or update records in external systems, read and write files, and query databases. Each tool is described to the model through a schema, a structured definition of what the tool does, what inputs it requires, and what it returns. The agent selects and invokes tools based on its plan, uses the results to update its understanding, and continues reasoning toward the goal. Memory is a critical dimension of agent capability that determines how much context an agent can maintain and how it learns from prior experience. Short-term memory is the agent's active context window, the running record of the conversation, tool calls, and results within a single task session. Long-term memory uses external storage systems such as vector databases to persist information across sessions, allowing the agent to recall facts, preferences, and prior task outcomes over time. Without effective memory management, agents lose context on long tasks and cannot build on prior work. Multi-step task decomposition is the planning capability that allows agents to tackle goals that cannot be achieved in a single action. When given a complex objective, such as researching a topic, writing a report, and emailing it to stakeholders, the agent breaks the goal into a sequence of subtasks, determines the order in which they must be executed, identifies which tools are needed for each step, and tracks progress through the plan. This decomposition capability is what enables agents to perform work that would otherwise require a human project manager to coordinate. Human-in-the-loop oversight is an essential safety and quality control mechanism in agentic systems, particularly for high-stakes or irreversible actions. Rather than operating with full autonomy, well-designed agents present plans for approval before executing consequential steps, request clarification when goals are ambiguous, surface intermediate results for review, and escalate to humans when they encounter situations outside their confidence threshold. Human-in-the-loop design preserves the speed and scale advantages of agentic automation while ensuring that humans retain meaningful control over outcomes. For essential terms that define how AI agents are architected and how they reason about tasks, the REACT pattern, short for reasoning and acting, is one of the most influential prompting frameworks for building reliable AI agents. Rather than asking the model to immediately take an action, REACT instructs the agent to first reason through the problem, articulating a thought about what it knows and what it needs to find out, then select and execute an action, and then observe the result before reasoning again. This alternating chain of thought and action produces agents that are more transparent in their reasoning, less likely to make errors from incomplete information, and far easier to debug because each reasoning step and its outcome are explicitly recorded in the agent's trace. Tool use is the capability that transforms a language model from a text generator into an active participant in digital workflows. When a model is given access to tools, described through structured schemas defining their name, purpose, and required parameters, it can decide autonomously which tool to call, with what arguments, and how to interpret the result. This capability, which Anthropic formalized in the Model Context Protocol and OpenAI popularized through function calling, enables agents to access real-time data, execute code, write to databases, and interact with any system that exposes an API. Tool use is the primary mechanism through which agents accomplish work that has tangible effects in the world. Agent memory is not a single mechanism, but a spectrum of approaches that together give agents the ability to maintain context and learn from experience. Working memory, the agent's context window, holds the immediate task history and is limited by the model's maximum context length. Episodic memory stores summaries of past interactions in a vector database, allowing the agent to retrieve relevant prior experience through semantic search. Semantic memory stores factual knowledge, product catalogs, documentation, policies that the agent can consult as needed. Procedural memory encodes learned workflows and tool use patterns. Designing the right memory architecture for an agent is as important as selecting the right model. Task decomposition is the planning capability that makes AI agents genuinely useful for complex, multi-step objectives. When an agent receives a high-level goal such as prepare a competitive analysis report and schedule a meeting to present it, it must decompose this into discrete subtasks, researching competitors, structuring the analysis, drafting the report, identifying available meeting slots, and sending calendar invites, and then sequence them correctly, accounting for dependencies between steps. Decomposition can be performed in a single planning pass at the start of a task, or dynamically as the agent encounters new information that requires replanning. The quality of decomposition directly determines the quality of the agent's final output. Let us now look at how AI agents are being deployed across industries to automate complex workflows, accelerate knowledge work, and deliver outcomes that were previously impossible to scale. Across research, software development, data analysis, and customer operations, AI agents are delivering measurable productivity gains by automating multi-step workflows end-to-end. Research and report generation agents are among the highest value early deployments of Agentic AI in enterprise settings. These agents receive a research brief, decompose it into search queries, retrieve and read source documents from the web or internal knowledge bases, synthesize findings across multiple sources, structure a coherent report with citations, and deliver a finished document, all without human intervention at each step. Tasks that would take a human analyst several hours can be completed in minutes at a quality level that requires only light editorial review, enabling organizations to produce research at a volume and speed previously impossible. Software development agents represent a significant evolution beyond code completion tools like GitHub Copilot. Systems such as Devin and GitHub Copilot Workspace can accept a natural language description of a feature or bug fix, explore the codebase to understand the relevant context, write the implementation across multiple files, execute tests to verify correctness, debug failures autonomously, and open a pull request with a summary of the changes. While human code review remains essential, these agents dramatically compress the time from requirement to working implementation and reduce the cognitive load on developers handling routine engineering tasks. Data analysis agents combine the reasoning capabilities of language models with the computational power of code execution tools to perform end-to-end analytical workflows. Given a dataset and a business question, the agent writes Python or SQL queries to explore the data, executes them to retrieve results, interprets the output, identifies patterns and anomalies, generates visualizations, and produces a written summary of insights and recommendations. This capability democratizes sophisticated data analysis, making it accessible to business users who lack the technical skills to write queries directly, while simultaneously accelerating the work of experienced analysts. Customer service agents that query databases and take actions represent a qualitative leap beyond the scripted chatbots of previous generations. Rather than following rigid decision trees, these agents understand natural language queries, look up customer records in real time, check inventory or account status, process refunds or order modifications, escalate to human agents when appropriate, and follow up automatically after resolution. They maintain conversational context across a session and can handle the complex, branching dialogues that arise in real customer interactions, delivering resolution rates and customer satisfaction scores that approach those of skilled human agents at a fraction of the cost. Let us bring together the essential points from our exploration of AI agents. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.